Firstly, we present its matrix form. At the same time, the circuit display of the Toffoli gate is shown in the figure. The qubits corresponding to the circuits with solid dots are control qubits, and the qubits corresponding to the circuits with a plus symbol are target qubits. The circuit with two solid dots serves as the control qubit. Later, we will explain in detail its computation process and working principle. The Toffoli gate has two control qubits and one target qubit. The gate is designed such that if the two control qubits are in the state Ket1, the target qubit is flipped. In other words, if both control qubits are in the state Ket1, the Toffoli gate acts like a classical XOR gate on the target qubit. The Toffoli gate is a reversible gate, meaning that the input can be recovered from the output. It is also a universal gate, which means that any quantum computation can be expressed as a sequence of Toffoli gates and single qubit gates. Toffoli gates can be used to implement various quantum algorithms, including quantum error correction and quantum search algorithms. They are also used in the design of quantum circuits and quantum processors. To implement a Toffoli gate, one needs to apply a sequence of single qubit gates and controlled NOT gates. Specifically, a Toffoli gate can be implemented using 3 controlled NOT gates and 5 single qubit gates. The exact sequence of gates depends on the specific implementation and can vary depending on the quantum computing platform. The table lists in detail the quantum state transformation rules. According to the calculation formula for the unitary transformation matrix of 3 qubits, as well as the quantum state transformation table, the matrix form of the Toffoli gate can be calculated. Additionally, below is another form of its transformation. Here we present an example to intuitively understand the effect of the Toffoli gate. Assuming that the Toffoli gate is applied to 2 ground states, the new quantum state is calculated. If both the 2 high bits are 1, it means that the low bit, as the target control qubit, will be flipped. After calculation, we can see that the result matches our expectation. To elaborate further, the Toffoli gate is a 3-qubit gate that performs a NOT operation on the third qubit if the first 2 qubits are both in the state Ket1. In the given example, the 2 control qubits are the first 2 qubits and the target qubit is the third qubit. Thus, when the 2 high bits are both 1, the third qubit will be flipped. In the calculation, we first apply the Toffoli gate to the ground state Ket110. Since the first 2 qubits are both in the state Ket1, the third qubit will be flipped, resulting in the new quantum state Ket111. Then, we apply the Toffoli gate to the ground state Ket111. Since the first 2 qubits are still both in the state Ket1, the third qubit will be flipped again, resulting in the new quantum state Ket110. This matches our expectation, as we predicted that the third qubit will be flipped when the first 2 qubits are both 1.